Welcome to our last lecture. Today we do a more practical part, so we see how we implement a large-scale PV power plant. What has to be considered, what has to be done, a lot of checklists and so on. So we see here the schedule, a timeline, so what has to be done first and last. In general, these tasks are united under the abbreviation EPC. It's an abbreviation for engineering, procurement and commissioning. So it starts with some consultancy, due diligence, master plan, a feasibility study, especially economic feasibility study, because you have to gain money with it, and you'll have to often lend money, and you have to convince the money lenders that the business plan is really okay, and I show you some things to consider. Then it's the concrete design and planning. So first it starts with a preliminary planning, then a conceptual design, then the permit application, because sometimes you have to make permits, you have to get permits from the utilities because you want to achieve a power purchase agreement called PPA, and the construction design. Then we go concrete into the procurement. So this is the tendering procedure. So you have to have the specification what the different components have to offer and so on. We discuss this a bit more in detail. Then the award of contract, material procurement. Then it's the concrete construction and the supervision of that construction, and the quality surveying, as-built documentation, construction, cost tracking, and then we have the startup, the start of the operation of the power plant. So you do a personnel training, operations manual, and a maintenance manual. Now also some special service related to it. I don't want to go into detail, but first you have to check whether the ground is stable. So you do a research on geology, hydrogeology, geotechnical engineering, soil mechanics management. Maybe you have also to provide some expertise in urban and environmental planning, and then the load-bearing structures. You have to show that the load-bearing structures will survive. Usually you say take a 100-year storm, and then the information management and GIS and automation via SCADA, project development, telecommunications, safety and risks, and then financial analysis. First, let's start with the site identification, the concept stage. So we have the identification of potential site, or sites plural sometimes, because you do a decision later after you have some different option and find out the best suited place. Then you have to first, before financing of the power plant, you have to look who pays for the project development, because you have also to pay some engineers and spend some time in this project development. Then you do a rough technical concept, kind of pre-concept. Then you do a pre-feasibility study that you assess different technical option. That means so you show for example, with storage or without storage, grid connection, some backup services, and so on. Then you do an approximate cost and benefit analysis, the permitting needs on the location. Sometimes you have to connect to the mid-voltage grid. Sometimes there is no grid connection point, and so on. And depending on the local legislation, this can sometimes not be underestimated. Then a market assessment. So who is a potential buyer of your electricity, or sometimes of your power plant if you want to sell the power plant. And then you start really with the feasibility study. So you do a technical and financial evaluation of the preferred option. So you just, instead of calculating all options, you I've selected one option which looks the most promising. Then you have different options for financing, whether it's a loan or sometimes you have a mixed structure, so you keep a part of the power plant and lend the power plant, or you just sell the electricity. And you already start the permitting process, because this can take an enormous amount of time sometimes. Then you have to get into contact with the bank, with the project development, to tell them what's the outline of your project, how are the risks and so on. Or usually they do the risk analysis on their own, and then you develop the technical concept. So go also with the second contact with the project development. Some banks they have some good experience and bad experience with some brands of modules and so on, and this has an impact on the interest rate. So if there is low risk involved, usually the interest rate is lower. If it's a new kind of technology, usually the risk is higher and you have to pay more interest rate. Then it comes really to the financing. So before financing, you have to have the permit that you are allowed to do that. So there will be some income. That's the most important stuff for the money lenders, for the banks. The contracting strategy, supplier selection, and contract negotiation. So how much is the warranty? Is the warranty on site, or you have to send the modules maybe to China? How fast is the reaction time? And then it comes really to the financing of the project. So a bank does or wants a due diligence of the financing concept, and then we go into the detailed design. So this you do a really implementation schedule, how many workers you need on site, how long will it take, which does it do in summer and winter, and so on. You have to really take care on all the details. And you do the finalization of the permitting process, so you give all the details and so on, and the timeline. When will the project be online? When will the payments for the purchased electricity and so on? And then with the bank, you come to a loan agreement with fixed interest rates and so on. And then finally, you can start with the construction. So you have to do construction supervision. Usually the bank wants an independent review of construction, so they want to make sure that their money is really safe, and they ask an independent institute to see whether this documentation you handed in to the bank is all reasonable and safe. And then it's a commissioning. So the plant is ready, and you interconnect it to the grid, and then you do before that you do a performance testing. So you measure the irradiance, and you measure the power output, and see what is the performance of the power plant, how much is the efficiency, and so on, as we did in several exercises. So also the bank usually has an independent entity for doing the commissioning, because they're bankers, they don't know so much, so probably they send an independent electrician or so to the site to supervise the commissioning. Okay, start from the beginning. So the checklists, the concept stage checklist. So we will see here really what has to be done in detail for a pre-feasibility study. So the project structure has to be outlined. Does the country and power sector provide adequate risk reward benefits to private investors? How long is it valid? Regulatory support and tariffs, especially for the duration and timeline of any incentive of solar power. Suitable site, identifying and taking account of site constraints. grid access, so proximity, capacity, and policy provision for access. Appropriate funds available to carry out the feasibility assessments. Someone has to pay for it because you spent several weeks or months to do that, and identification of off-taker and an available infrastructure to take the power generated. Usually you call this power purchase agreement. So for the prefability checklist, there's a checklist here. The assessments of the site and the boundary areas, including access permissions and the restrictions. Conceptual design completed during consideration of technical options, technology options, and their financial impacts. So for some sites, you have to consider there couldn't any big reflections on the module surface because there's an airport there. Sometimes they say, okay, you have to do a tracking system and so on. This really depends on the local conditions. Appropriate cost of land, equipment, delivery, construction, and operation identified along with the predicted revenue. An indicative energy yield completed. So if the size of you have this site conditions, the temperature and so on, and you can do a temperature estimation with some software to find out the operation temperature. And you have the irradiance tables, which I showed you in the first part with either with the software Meteornom or GIS or with ground measurements and so on. And so you can give some first estimations of the energy yield and also the financial yield. That's quite important. And identification of the anticipated electricity tariff to be received and review of expected terms and conditions of PPA in the relevant market. So sometimes, as in Germany, they buy any kilowatt hour generated independent of the time. Some other countries, they say, okay, you have to have some certain number of full load hours during the year, or they give different tariffs for the day and nighttime and so on, or and so on. So this really has to be investigated. And then you carry out a high-level financial analysis and the cost and likelihood of achieving grid connection in the required timescales. So this depends on experience. So just if you know the utility and you know that they're working slowly or fast, and so you can make a guess about whether the timeline is realistic or not. Part 2 here are main environmental constraints identified along with potential deal breakers. So there could be a change of government, could be a lot of things. So you just this is depends also the owner of the utility may change, and he doesn't want that power purchase agreement anymore. Assessment of current and potential future regulatory environment completed. So that's also related to the upper. So you have to make a future estimation what will happen in the future. So when you finish your project, will the contract still be valid? Sometimes if you have a power purchase agreement in a foreign country, it's usually paid in local currency. And if there is a chance of a high inflation, the money you get isn't so much worth anymore. Sometimes there's an inflation compensation for that, or you fix the power purchase agreement in euros or so. Then an initial concept of the project's legal and corporate structure. Usually you form a company of the power plant, so it's more easy to sell, rather because you have either the power plant and the ground, and usually you make one package out of it and sell it together as a company. Also usually taxes are lower than to sell land and then equipment, and usually it's called special purpose vehicle. That's the construction. And also you have to provide solutions to the project challenges. So also the bank will interview you and ask you a lot of things. What are the challenges? What are the possible constraints? And then you have to provide the solutions. Permitting requirements and the costs for that. A preliminary project timeline workflow showing spacing of key activated drafted. Now we come to the feasibility stage. Here also another checklist. First part. So you have now a detailed site plan produced. Usually it's quite easy if you have flat terrain. Sometimes this is really getting cumbersome if you have some hills on the terrain. And as I presented in the first lecture with the irradiance and the shadowing, this to make sure that a large part of the year you have no shadowing, and if there's shadowing, how much will that impact your energy production, and depending on your power purchase agreement, if they say you have to produce energy through the whole year, is there an impact on that, on the consistency of the power production and so on. This is also related here, solar resource assessed, including assessment of shading. That's exactly that. And the environmental characteristics that may affect the performance identified. So is there, for example, a lot of sand which will accumulate on the modules, or dust? Is an industry nearby, or are there trees which leave the leaves during winter time? So you have to make sure that the modules are cleaned, and so on. There could be all other constraints. For example, recently was a project in Switzerland. There was a lot of hail, exceptional big hail. So you have to purchase heavy-duty modules which can withstand this heavy hailcorns. A detailed review of environmental and social considerations are conducted. So just here, what is the impact on the environment of such a power plant? Usually that's less critical than, for example, at wind power plants. And social consideration, it's also, for example, if you have a solar pumping system and there's already a pumping system installed, and the original operator is without work, and so we will be against your project, and so on. This has all to be considered. Detailed review of the required permits and the licenses. Then the assessment of CapEx for technologies and supplier option. So the cost benefit for options and project locations is completed. So this is for the bank the most important part. They want to see the return. Pre-application discussions with relevant consenting authority undertaken. So for example, a local authority could be a major, or somebody is responsible for the land and so on. Initial consultation with key stakeholders, including from the community, completed. So sometimes the community is really nervous because they think photovoltaic is ugly, and so you have to present them already detailed plans and to show that's not the case, and so on. Sometimes as a wind power, the community wants some money for that because you change the landscape and so on, and this has also been negotiated. Then very important is the grid connection assessment completed. So if you cannot put your electricity on the grid, so this is the whole project is in question. The predicted energy yields are established, and the further assessment of the anticipated electricity tariff is undertaken. Financial analysis is carried out, preliminary financing planned. The project implementation plan developed. So just what are the time frames, which task takes how long time, and some reserves. options agreement for land access when required or secured. So it's not only the land where you put the power plant, you have also have an access to the land to drop it off for maintenance and so on. So if you sell the land later, maybe you don't have access anymore to carry out repairs and so on. This is also be thought about. Evaluation and concept of commercial structure of the project and project companies are carried out. This is what I mentioned before already, just with a special purpose vehicle. And the checklist for permitting, financing contracts, first part, preparation and submission of relevant permit and licenses applications. The environmental and social assessments as required are completed. Grid connection application prepared and submitted. The grid connection agreement signed. Review of design and permit consent conditions completed. Contracting strategy approach determined. Financing structure decided. Financing secured for the project. Community or stakeholder engagement completed. Solar PV tender documentation prepared. So as I mentioned before, just you have to give all this technical specification, how big the hail can be or has to be for the modules until it is destroyed. What wind loads are there? Do you need any special coating if there's dust accumulation? And so on. How big the foundations have to be, which depends on ground and so on. Supplier selection and ranking. So you just not use one supplier, you use several, usually minimum 3, and then you do a ranking depending on quality and price and whether they can keep the time schedules. Then the power purchase documentation prepared. Then the operation and maintenance concept and contracts are prepared. So the owner's engineer tender prepared. The relevant insurance procured and contracted, but against theft, against exceptionally storms and so on, or earthquakes. What happens then with the power plant? Is there insurance or not, and so on. This is all to be evaluated or procured and then finally contracted. Tendering and evaluation of bidders for all contracts carried out. Contract negotiations completed. Then a bank grade energy yield completed, because the bank wants to eliminate risks, so they want to really it's not only technical energy yield but also financial energy yield. So they just always use worst case conditions. What happens if there's inflation? What happens if the power plant is degrading in power output? Usually they even provide an independent entity to carry out that. So usually are called bankability. A detailed bankable financial model completed. Transportation analysis carried out. Sometimes such locations are really remote and you have to think about the logistics, how to transport them. Is it reliable? Some streets, if you go in the tropics, are not accessible during rainy periods and so on. All land and access agreements are finalized. This means that you have to get access to the land, at least for the whole operation period, which was formerly 20 years. Now it's more going up towards 25 or even 30 years. Project risk analysis completed. This is very important for the bank. So they, as I told you, they always take worst case conditions, and for the power, the tolerance for the power of the modules, the time what could be happening, the inflation and so on. This is all in such a risk analysis. Then the power purchase agreement is finalized by the buyer, by the off-taker. Detailed project implementation plan finalized, and technical and legal due diligence completed, if required. Sometimes it's not required. Now we come to the detailed design phase. So you have a detailed check of products, components, services, and suppliers. So we have first basic standards. So you say, for example, the module have to be adequate to IEC or have to be certified for IEC 61215, or additional requirements, for example, PID, or if you have a farm nearby to be ammonia resistant, or if you are at the seashore, you have to make sure the module withstands salt mist and so on. So you have to choose an adequate norm for that and say, okay, this has to be a part of the contracts with the supplier. Then there may be additional requirements, for example, by the government. So you have to show, for example, that the company has long experience, exists for some time, and so on, and is able really, in case of problems, even to withstand some crisis. Also for the banks or investors, or for the utilities. So grid interface, so how much harmonics can be fed into the grid? What happens if the grid is shut off? Will you be paid then, or you have to immediately shut off the power plant, or sometimes there's a regulation with a fault riding through. So the power plant is keeping up the operation of the power plant for some milliseconds and so on. It's just to override power failure, and then helps to keep up the grid running and so on. Also for metering, so you have to make sure that the meters are all certified and calibrated. Sometimes there are even requirements that you have to choose some local produced metering devices, so they are sure that the metering is correct. Here the checklist for the main components. So for the module, you have to have a supplier identification and track record checked. So you make sure that the warranty really can be fulfilled. If you have a completely new company which exists only a couple of months, but you want warranty for 25 years, that's a bit hard to secure that. Then the certification, for example, IEC 61215 or 61730 for the safety requirements, and so on, as I explained before. Then you have the power product and power warranty terms. Usually you say that you have to, at least after 25 years or 20 years, depending on the conditions, have the original power output, so the power degradation is allowed to be only 20%. Sometimes it's useful to have a third-party warranty insurance in case the manufacturer goes bankrupt and so on. Technology suitable for the environmental conditions, for example, high temperature, lots of diffuse radiation, humidity, but more severe is just salt mist or dust accumulation, or for example, we got a project in Bolivia. This is very high up in the mountains, and there is really high UV radiation there, and the equipment has to be suitable to withstand that. Shading conditions, so if you have shading, so the number of bypass diodes is relevant. If you don't have shading, so you have a large distance between the modules, and there's no other obstacles, that is less relevant. And then the power tolerance, formerly it was a plus minus 3%, so if you had a 300 watt module, so there could be plus or minus 3% of the power output. Nowadays it's more, because usually banks takes worst case, so they always say, okay, it's minus 3%, and so they automatically calculate it with a power of 91 watts, so minus 3%. Nowadays it's a zero minus tolerance, so they say, okay, the module has at least 300 watts for 300 watt modules, maybe a bit more And for the bank, worst case, okay, 0. And then the 300 watt module is calculated as 300 watt. And if you generate more, okay, everyone benefits from that. Let's come to the inverter. So the checklist, so the suitable capacity is for the project size. So you saw this one, transparencies. In Europe, the modules seldomly achieve the power output under standard test conditions. So you may undersize the inverter a little bit without many losses. For other countries, it's different. So you're quite close to the standard test conditions, and so you have to choose the right size of the inverter. Then it's important every country has its own national grid code, so it has to be compatible, and you have to have the correct certificate for that. As I already mentioned, could be fault riding through, the harmonics, and so on. There are a lot of requirements. Whether the inverter can be switched off remotely depends also on the size of the project and so on. This has to be checked in advance and is quite cumbersome. Then the supplier identification and track record checked, same as for the modules. So you want to make sure that you have in 20 years still someone from the company who may repair the inverter, or even better, have a warranty for that. But usually the warranty for inverters determines standard for 10 years. Don't know why. If the whole power plant is 20 years, there's only 20 years warranty for the modules, but not for the inverters. Usually you make sure to negotiate a 20 years warranty for that. Also the certification. So this is much more standards than for the modules. As I mentioned, if you have the IEC 61215, you covered most of the circumstances for inverter. There are much more norms, and depending on the local conditions on the country. Yes, and then product supply terms and conditions in line with the market standards. The technology and model is suitable for the environmental conditions. So either outdoor inverter, or if you have the possibility to put it indoor, then you have to make sure that the temperature doesn't get too high indoor. But usually indoor inverter is much cheaper than an outdoor inverter. And then you have to take a look at the possible temperature. Usually they say just between -20 and 40 degrees, but if you go in the tropics, you easily reach 50, 60 degrees. So you have to make sure that the inverter is able to operate under that conditions. If you have thin film modules which have a lower current but higher voltage, you have to make sure that your inverter is withstanding that. Sometimes, depending on the requirement of the module manufacturer, they have to be grounded or not grounded, and the inverter has to be suitable to do that. And the efficiency we talked about when in the inverter section, we talked about the European efficiency, about the efficiency of the California Energy Commission, and so on. So here are the different test conditions for the module. As I mentioned already, the most important is the IEC 61215. This is the crystalline. This is for the crystalline terrestrial PV modules. It's called Design Qualification and Type Approval. It sounds like nothing, but it contains a lot of tests. So this includes for thermal cycling, humidity, freezing, mechanical tests, twist, hail resistance. The standard certification uses 2400 Pascal pressure. If you install your modules, for example, in the Alps, then you have to make sure that there is an extended pressure resistance. For example, here 5400 Pascal. So it can withstand either higher snow loads or wind loads. Then the IEC 61646. This is for thin film modules. It's very similar to the IEC 61215 certification. Here they have additional tests, and not so much additional tests, even less tests, because the power output determination at thin film module is much more complicated, because you have to do light soaking in order to find a stable power output. and this is quite cumbersome, costly, and consumes a lot of time. Then we have the IEC 61730, which is very similar to the UL 1703. This is a module safety qualification. So here, this is the safety classes which come out as a result of these tests. It's also against, usually that's already part of the IEC 61 to 15, but there are additional, the 6003 664 -4-41, protection against electrical shock. So usually you have this one, but I hardly know someone who is using that, because usually this one includes, and together with this one, most is included there. Is more important is the 61701. This is a resistance to salt mist and corrosion. So if you install your module in the Alps, that is totally irrelevant. But if you install it close to the seashore, that's really relevant. Then you have the 61853. That's quite interesting. That's a PV module performance testing and energy rating. This has been development for a long time, but so you have some hints if you have, for example, temperature or different irradiance level, for example, weak light performance and so on. This is included all there. Yes, this is a pending issue. System voltage durability for crystalline silicon. This includes the PID test. So I think now it's out. There was a big discussion about the temperature. The higher the temperature, the more sensitive the modules are to that. Also about the humidity. I think they agreed now to 85% and 85 degrees, which shows the problematic modules very quickly. Before there was under discussion 60 degrees only, which requires more time, and the modules appear to be more PID resistant than they really are. Then they have the EC sign, so that's not only for PV modules, that's for any equipment imported into the European Union. So this is about health, safety, environmental requirements. You have to have it. It's not very harsh conditions, but it's a requirement. And then the UL 1703. So this is electrical safety, but also fire safety. And this, as I mentioned already, this is very similar to the IEC 61730. If you want to make a project in the US, you have to provide the UL certification. The IEC is not enough, even if they are very similar. So now we come to the inverter and grid interface. So there's a standard EN 61000, so 61000-6-1, and then the year 2007. It describes the electromagnetic compatibility, so this immunity for residential, commercial, and light industrial environments. Then you have here some differences between industrial, residential, and so on. So emissions. So this is the emission on radio frequencies and so on. So there's no radio disturbance by that. Then this is more interesting here. You have here just for the information technology equipment. So radio disturbance, yes, that was the upper one also. And then you have the 50178. So this is the standard for electronic equipment used in power installations. Then you have a specific one as a 61683 for photovoltaic systems. And this is also, as I mentioned, the UE norm, the procedure for measuring power efficiencies. And this is also very important for description of the characteristics of the utility interface. So you have to, because these are sometimes changing depending when the next edition, you have to make sure that you have the latest standard, and this has to be in agreement with the requirements. Sometimes the utility, they stick to an older requirement. So an older year, you have to just make sure that you can use apply the latest requirement, or whether they require that you stick to an older standard, which was usually not often the case. Safety of power converters for use in photovoltaic system, and islanding prevention measures for utility. So if the grid is switched off, what happens then? And you have to, this has to be certified by that norm 62116. Usually the power output, the voltage output by the inverter is limited, 600 or 800 volts, and you want to interconnect it to the mid-voltage grid or even the high-voltage grid. You have to apply a transformer, so which transforms, for example, from 600 volt to 10,000 or even 20,000 volts. And this is a selection checklist for the transformer. So you have here the transformer has to be suitable for the project size. It has to be comply with the national grid regulations. You have to have a supplier identification and track record checked. That, as I mentioned before, the minimum certification obtained. I have a product warranty terms and conditions in line with the market standards. While the bank is usually financing the power plant as a whole, they always take the worst conditions, so they take the lowest warranty. So you have to make sure that all components have the required warranty periods. So for example, 25 years. And so you have to check that the warranty of the transformer is also that. Usually electronic company don't have that. Maybe you have to purchase an extra warranty insurance. Suitable for the environmental conditions, same as before, inverter and modules. So outdoor, indoor, ambient temperatures and altitude, maybe also dust, because when the transformer is artificially ventilated, there can be some dust accumulation and so on. Or altitude could be either temperature change or ultraviolet radiation. And also the efficiency plays a role, and usually not a big issue, because most modern transformers, they just lose a 0.5% or so. It's usually not a big deal breaker. And a load and no load issue in line with the market standards. Mounting structure. So the mounting structure, also the same, supplier identification and track record checked. Usually these are custom, or often, not always, but often custom made by local companies. So it's quite hard to check the quality control of the manufacturer, or you purchase a pre-fabricated module mounting structure and so on. Also, there's some certification issues. Product, go back to the chapter of mounting structure, they mentioned it there. And the product warranty terms and conditions in line with the market standards, and it has to be suitable for the environmental and ground conditions. For example, thermal expansions, marine environment, soil acidity, and so on. Also, if you combine different materials, for example, you have the foundations on concrete, then you put in a steel bar, and on the top there is aluminium, and there could be some severe corrosion between these two metals. If there's, for example, acid rain and so on, then they corrode very quickly. Then the general design checklist. So quite obvious, the tilt angle and orientation of the PV array suitable for the geographical locations. Or even if you want to, for example, produce more power during winter time, you choose a higher tilt angle, or you put it more towards western, you have more western orientation, so it's more producing in the afternoon and so on. As we already heard in the lecture, so the inter-row distance is relevant for the shading. So you have to choose an adequate inter-row. This also depends on the height due to the tilt angle and the size of the modules and so on, and the usual location there. when it's close to the equator, then sure the sun is always more perpendicular. If it's more towards the poles, then during wintertime you have more shading, and then you have to increase the distance between the rows. Shading of obstacles or nearby project. This could be some buildings or trees and so on. We have to also take into consideration if you have young trees there. In 15 or 20 years, the trees may grow and then cause shadowing then, but not in some simulations program like PV Soul, they included that. You given the type of tree, and it already calculates this, the future size of the trees and the possible shading. The PV string size suitable for inverter under the side of the environmental conditions. So as I mentioned already, we had it also in the lecture and made an exercise about it. So if you have very cold conditions, then voltage may increase, and in order to keep within the standards, for example, you have to keep below 1000 volts under all conditions, and so you only can interconnect a certain amount of PV modules in series. For example, 21 module. If you would have 22 modules, even under standard test conditions, would be below 1000 volts. But if you have very low temperature, for example, very cold winter morning with minus 10 or minus 20 degrees, then voltage increases, and you then past this 1000 volt limits, and then the module is out of certificate, or the PV power plant is out of certification. And this is to be checked. It even may destroy an inverter depending on the tolerance of that inverter, but there could be even some destruction of some components. Also, you have to make sure that the possible operating conditions stay within the range of the maximum power point tracker of the module. As I mentioned before, the transformer has to be correctly sized. Combiner boxes, so you have to make sure that new humidity enters and new dust enters. So there's a IP rating, for example, IP68 or something like this. This makes quite sure that no rain and no dust can come in. The DC and the AC cables are sized correctly. We did this already in the exercises. And the low voltage and high voltage protection equipment, so that means fuses. Fuses also, we have to distinguish between DC and AC. The switch gears, same issue, and circuit breaker, same issue. And the suitable grounding or earthing and lightning protection designed for the site-specific locations, also the national requirements. Civil works, so that's the foundation and the drainage for rain and so on. So you have to make sure that no water enters the hut where the inverter is and so on. So you have to make that sure. And depending on the local, if you have in the desert, you have less problems. But if you have an area where you have a monsoon period, this can cause some serious problems. The monitoring system, so you want to check whether your modules and your whole system is performing well. You have to make a monitoring system. As mentioned when we discussed about microinverters, they allow even monitoring on on a single module level. If you have strings or even a central inverter, you can. It's hard really to distinguish which part of or which exactly component failed if there's some problems in the power plant. In a security system, just you have to make a fence perhaps there, so nobody can steal modules, or it could be some vandalism and so on. This depends on the requirements by the insurance provider. It has to be accepted by them. Sometimes a really expensive project, they send someone there to check that. Now we come into the phase of detailed planning. So first you start with the first chapter, solar resource assessment checklist. So you have a variety of solar resource data sets we'll discuss a little bit later. You know already from the first lecture. And best would be if you have at least 10 years of data. Sometimes you don't have this data available, so sometimes you have only from 1 year, and you have to check whether this changes something or still accepted by the utility or by the one who is, or by the banks and so on. You can use satellite-derived data or data interpolated from ground-based measurements. Sometimes there is a ground-based meteorological station in some distance, and you can interpolate that. Usually the programs do that already. For example, the Meteornorm software is able to do that, so it takes several close by measurement stations there and interpolates that. And then you have to the site adaptation, the calibration of satellite data. We found out that satellite data differs because you can only see the reflected part from the ground, and we found some years ago some up to 20% difference in that. Maybe this improves. This depends also on the site location and so on. So best is to calibrate it, to put a pyranometer there and check for that time point the data given by the satellite and see whether these two irradiance values agree to each other. Yes, there's some algorithms have been placed to convert the global horizontal irradiance. That's usually what you measure, data you get from ground-based measurements from meteorology station, but also from satellite data. They don't have data really for tilted areas, and so this is interpolated by some algorithms. And very important to do an uncertainty analysis. How much are the possible errors? How much is the tolerance by the pyranometer? What are the tolerances by the algorithms, and so on. Here, the different software to do a solar resource assessment. So there is Solar GIS. So this is quite often used. This is available between 60 degrees north and 50 degrees south, with a relatively high resolution of 250 meters. And it's calculated from satellite data and digital terrain, atmospheric data and digital terrain models. Solar resource data are available from the years 1994, 1999, or 2006, depending on the region and so on. And a time resolution of 15 minutes. And this database has been extensively validated. That's important, of more than 180 locations globally. This 3-tier don't know so well, so this is also quite similar. And here you see 120 reference stations across the globe with a standard error of global irradiance of 5%. HelioClim, this is also from commercial satellite derived. There's not so much given about the tolerance. What is very often used is the Meteornorm database, and this is specially made for photovoltaic application. So you can even have some tilt angles there, and they calculate the irradiance on the tilt angle and divide between direct and diffuse irradiance in case you have concentration things. And yes, can look up on the website. So what's the actual? I think the actual version is 8.0. This is commercial. A free software is from the NASA Surface Meteorological Energy Data. So you have here data of a grid of 100 by 100 kilometers. So it's much more raw than the Solar GIS, which is 250 meters by 250 meters. But it's for free, so it's also quite good, evaluated for 22 years. And it's good for preliminary feasibility studies. Because for detailed, they have too low spatial resolution. Then the PVGIS, so that's from the European Union. It's for free, and it's for Europe and Africa, as far as I know. And they included also some temperature models, so they also include the possible yield of PV panels, and so you they provide maps where you find exactly the energy output per kilowatt installed of conventional photovoltaic crystalline PV modules. So that's quite comfortable, and this is okay. Resolution is better than from NASA, 2.5 kilometers only, but not as good as Solar GIS. But it's quite helpful, and the best thing is it's for free. But if it's outside, so in the Americas or somewhere in Oceania, it's not really suitable. But for Africa and Europe, it's a very good option, and Middle East. So now the operation and maintenance contracting checklist. So legal and technical advisors engaged to advise on form of contract. The O&M contractor is suitably experienced on a similar scale, planned and familiar with the technology. The performance guarantees included to allow owner to claim liquidated damages, LDs, in the event of low ability or low performance ratio. Payments are made to the contractor in arrears to allow for deduction of any LDs over the corresponding period. LDs size to be a genuine part of pre-estimate of losses likely to be occurred. Rules of spare parts management are clearly defined. Contractor is responsible for replenishing stock and ensuring original level is maintained, and the rules for subcontracting is clearly defined to ensure principal contractor is that he is fully responsible for all subcontractor works, and the O&M contract requires the contractor to maintain all equipment in line with the manufacturer guidelines to ensure that all equipment warranties remain valid. That's also important. If you modify something, then the warranty may not be valid anymore, and this is a serious issue. Preventative maintenance regime defined in a contract is comprehensive, helping to minimize the need of corrective maintenance. So if you have preventive maintenance, you usually don't have to switch off the power plants, and it's quite foreseeable. But what happens if you have corrective maintenance? Something happens, and you don't know which component has to be substituted, and it takes more time. And during that time, you also lose energy yield and money. Now we come to the construction phase checklist. So required, we have a contract fully signed and reviewed by a technical advisor covering all possible interfaces. Design documentation completed. Detailed program of works is completed. The quality plan is completed. The health and safety plan is completed. The monthly reporting is in place. All consenting, permitting, and financial requirements are in place. Commissioning and testing plans as agreed by all parties, detailing requirements and any tests needing witnesses or sign-off. Recommended. The other one was just required. One was just, but was required. Now this is only recommended. So interface matrix drawn up, so it's more easy to overview the possible interfaces. Deliverable schedules prepare for all documentation, so it makes also much more easy to handle. A weekly look-ahead program is in place. Risk register detailing all potential risks and mitigation measures in place. Environmental plan completed. Monthly report structured completed. Matrix detailing the requirements and due dates prepared. What are common mistakes of that? So module installation. There could be an inadequate number of clamps used or incorrect positioning, resulting in reduced module bearing load capacity. Usually the positioning of the clamps, also the type and the area of the clamps, is given in the module data sheet. If you modify from that, also the warranty may not be valid anymore. This is what I mentioned. So modified or wrong type of clamps. So there could be an inadequate spacing between the module, compromising integrity of the fixing and leading to invalidation of the warranty. Module clamp bolts initially hand tightened and then tightened to the correct torque after period of delay. There's a risk that strong winds can blow the modules off if, the structure if the time lag between assembly and tightening is too long, and the tightening of bolts should occur shortly after assembly. Over tightening of clamps, so some don't have a torque limiting tools there, and they may destroy the clamp or even damage the modules. So, for example, the the coatings then of the clamp, but maybe even of the module. Damaged or scratched modules due to poor installation technique. The front and rear surface modules should not come into contact with a support structure. This is also due to the technical, to the electrical safety. It's given that the module can be only fixed via the module frame, and it really stays away from any metallic material, especially the back part. Mounting structure. So as I mentioned already, dissimilar metals are not insulated from each other, leading to material incompatibility issues in the form of galvanic corrosion. Isolation solutions such as neoprene pads can be used. Deformation of the mounting structure during piling process, compromising galvanization or structure. Piles installed out of position, leading to piles and steel sections being forced or bent out of alignment in order to line up with framing sections. Civil works, poor dust suppressions are leading to excessive accumulation on dirts of modules. Missing or delayed perimeter fencing leading to animal or human intrusion. A fence should be installed prior to construction commencing. Drains becoming blocked with silt or during the earthworks. There could be some flooding then. Drains are becoming blocked. Yes, this was before. And inadequate surface water run management during construction, leading to delays caused by flooded or waterlogged sites. Excessive load bearing capacity of exiting public tracks, causing damage. Lack of leveling works after installation. The integrity of the controlled environment within equipment enclosures or housings can be compromised if not installed correctly. Examples of common issues include unused glands not sealed or replaced with dummies, unsealable cable conduits, damaged or missing gaskets on entrance doors, unsealable cable trenches leading to inverter housing, so the inverter can be even flooded or filled with dust to these cable tubes. A water ingress due to any all of the above leading to a humid atmosphere causing corrosion damage to electrical components. Environmental monitoring. Incorrect positioning of the environmental monitoring equipment can lead to inaccuracy during a performance assessment. The most common reasons for these inaccuracies are pyranometers are not positioned at the same tilt angles of the modules. As I mentioned, you could apply an algorithm, but it's not very accurate, so you have inaccuracies there. A pyranometer subject to shading, dust accumulation, and moisture ingress, causing a reporting of elevated performance ratio elevation. So it's quite interesting. So if the pyranometer is shaded or has a dust accumulation, you do not see the problem immediately because you perceive reduced irradiance but still acceptable power output. You think your system is performing very well, and that's quite dangerous because the truth is otherwise. Cable management. So cables crossing over sharp edges or mounting structures without suitable padding, insufficient labeling of cable endings, long unsupported spans due to an insufficient number of cable ties, cable banding radius is too tight. This could lead to breakage of the insulation or even of the core of the cable, so the copper and so on. Inadequate cable burials depth, inadequate conduit cable protection, signage, basic information requirements which are often omitted include general health and safety requirements, including emergency contact numbers, lack of warning labels on electrical components. So if there's high voltage, you have to make that clear by labels. Lack of warning label on perimeter fence. So you have to make clear that nobody can enter, or if you have an electrical fence, you have to advise that. Support structure identification and labeling. Spare parts. The permanent storage of spare parts is often not available when such components are delivered to the sites, leading to damage from poor temporary storage conditions. Documentation's actual plan of sometimes the plan is modified and you don't have an actual version. So that's include all components which are inside. So the detailed wiring plans, including all the properties of the wire, such as flexibility of the wires, UV stability, thicknesses, and material of the conductors. So it could be either copper or it could be even aluminum and so on. And also backup. So maybe these plans get stolen or get lost or burned or whatever. So you have to make sure that you get backup because they are really important. Here are some hints for the documentation. So what you have to for the array. So this is a module types, the number of modules, the number of strings, modules per string, the PV string information. So string cable specifications, the size and type, string overcurrent protective device, which is a fuse or a diode, and a type of voltage current, and blocking diode type. So usually call it string diode. And nowadays it's not often anymore necessary, but formerly it was required. Array electrical details, so the array main cable specification, the size and the type, array junction box locations where it's applicable, the DC insulator type, location and rating, voltage and current, array overcurrent protective device where applicable, type, locations, rating. We did this already in the exercise a bit about the dimensioning of the cables. Earthing and protection devices, so details of all earth and bonding conductors, size and connection points, details of array frame equipotential bonding cable where fitted, details of any connections to an existing lightning protection called LPS, details of any surge protection device installed. Both AC and DC lines include location, type, and rating. Usually these are installed either close to the inverter or as connection boxes we saw in the lecture. The AC system, so here you have the AC isolator location, type and rating, AC overcurrent protective device location, type and rating, residual current device location, type and rating, and so on. Grid connection details and grid code requirement, that's really important. And this has to be in agreement with the utility. Data acquisition and communication system. So this is data for the communication protocol, wire regment, sensors. I would add here also passwords and so on. And so here you see such a structure. Here you have here the PV array, then the low voltage to mid voltage transformers. Then they have the mid voltage collection switchgear, and then you may go to the high voltage, and you need a high voltage transformer, and then here you are at the grid. These are the voltage levels. So usually high voltage is above 33 kilovolt, and mid voltage is from 1000 volt up to 33 kilovolt. And low voltage is below 1000 volts, so this is usually where you interconnect your PV power plant. There is some discussion whether it should be changed to 1500 or even 2000 volts. Here you see the operation, the monitoring optimization. So you see the meteorological sensors, most important the irradiance sensor, but also the temperature sensor and wind speed and wind direction. Then you have operation data of the inverters, the meter, feed-in meter. Sometimes you have a DC meter also, the power transformer and the grid. And this SCADA system, it's called a System Controlled and Data Acquisition System. It provides real-time data, but also historical data, alarms. In case there is a problem, it sends a SMS to operator, or email or a fax, and logs some events. You have here the monitoring sensor, so you have here a connection to the sensors either by DSL or a wireless via GSM, via the GSM network. And then from the monitoring thing, go via internet, and then you can basically in any part of the world you can check that via the web interface, monitoring visualization. And usually also banks are quite interested in that to see how well their investment is performing. Performance optimization. So the loss, and then we talk about mitigation measures to optimize performance. So in case of shading, so you have to relocate or choose locations without shading obstacles. Ensure that the plant has sufficient space to reduce shading between the modules. This was discussed already twice here, and have a robust operation and maintenance strategy that removes the risk of shading due to vegetation growth. So you have a gardener there on something like this who cares about that the vegetation isn't causing any performance issues. The incident angle, anti-reflective coating, textures glass, and so on. Tracking low irradiance. So this is also just calculate already how much is the gain by anti-reflective coatings and so on. Tracking low irradiance. So you choose modules which offer a good performance at low irradiance level. That's usually if you have a high RP. This bypass current, this bypass resistor. So if it's really high or best non-existent, you have quite a good low irradiance performance. Module temperature. Choose module with an improved temperature coefficient. That's often not possible because a crystalline module is almost the same in the vicinity of minus 0.4% per Kelvin. But you can take care on a good ventilation and a good distance to the ground or to the roof, and this helps to lower the operating temperatures. The soiling, choose a module less sensitive to shading. Okay, with the soiling, this is same as shading. It can lead to some problems. So just if you have enough bypass diodes, this helps. Ensure suitable operation maintenance contract that includes an appropriate cleaning regime for site conditions, and module quality. We discussed this already with a low tolerance or positive tolerance. Yes, is for the banks, as I told you, they always take a look at the worst case, and if there is if you have a zero tolerance to the lower part and just positive tolerance, then they take the number plate value for the power under standard test conditions. Module mismatch, so you sort the module with similar characteristics in the series strings. When possible, avoid the partial shading of a string, avoid variations in module tilt and angle and so on in the same string. If you use module inverter, this isn't a big problem. DC wiring resistance we calculated already in the exercise. This also for the inverter performance. Yes, you have the high efficient inverters, and they have to be correctly sized. AC losses, also the sizing of the cables and so on, and high efficiency transformers. Plant downtime, that's important, that you have to really make sure that the operation and maintenance team is quickly there and allow a very quick repair of the power plant. So you have to make sure that they have spare parts for it available quickly. So you don't have to wait for weeks until you get a spare part, and so on, to keep the power plant constantly running. Grid availability, it could be also an issue in some countries. A grid is failing, and so you can't feed anything in the grid, and sometimes you don't even get money for that. So although the grid has to be stable and has strong and has the potential to absorb the PV power, but usually the utility is taking care of that. Degradation, so sure you choose modules with a low degradation rate and a linear power guarantee. So you have a guarantee, for example, after 25 years, the module is still able to deliver 80% of its initial power under standard test conditions, or even better. A maximum power point tracking, yes, you have to choose high efficiency inverters, and can add to this that they even fast tracking and have a global tracking. Sometimes if you have shading, there could be 2 maximum power point on the IV curve of the modules, and it has to find both and then select the actual power point which offers most of the power. So on. Remember when I talked about this in the bypass diet lecture, that how the IV curve look like, and the maximum power point tracker has to be able to deal with that. Curtailment of tracking, so ensure that the tracking systems are suitable for the wind loads to which they are subjected. That was it. So most of this part I took from the Project Developers Guide, Utility Scale Photovoltaic Power Plants from the International Finance Corporation. That's a part of the World Bank Group from 2015. Usually if you take care on the required checklist, there shouldn't be a problem in just realizing your project. Thank you very much.